Good morning, everybody. Thanks for coming here. Thanks for being here with us today. We have a very special event today. We are launching Spectronaut 17, featuring directDIA Plus. directDIA Plus makes Spectronaut 17 one of the most impactful releases that we had for Spectronaut so far. And you will know more about that in this seminar. So today I'm going to start giving a short introduction about Biognosys in our offering. And then we have Lukas Reiter, our CTO. He will give more information about what's new in Spectronaut 17 and what makes it much better than the previous versions. Then we have Jesper Olsen, professor at University of Copenhagen. He will show how Spectronaut 17 outperforms previous releases and also other solutions in the market on different applications. So let's get started with the introduction. Biognosys is a company offering services and products for proteomics applications. We are a CRO, and we also provide kits and software for proteomics. We've been around for more than 14 years now. We are inventors and developers of unique solutions for proteomics, and we have one of the largest facilities of its kind in the world. What I show here is the offering of our services. So we provide services in contract research mode, and we have different type of platforms. We have two. That was not what I wanted to show. We have TrueTarget for target deconvolution, drug target deconvolution studies. We have TrueDiscovery, basically unbiased discovery proteomics approach. And we have TrueSignature, which is our targeted offer for small panels or not so small panels. And what brings us here is the offer for kits and software. We offer kits. We offer kits for sample preparation, quantification, and quality control. And we offer as well, as most of you probably know, we offer software for different applications. Spectronaut for DIA, SpectroDIA for targeted proteomics, SpectroMine for isobaric label quantification, and for label-free quantification in DDA mode. And we also have Quick, which is our solution for quality control and mass spec facility monitoring. One thing that is common to all of our software is that they are outperforming all solutions in the market. They are reliable and trusted by the scientific community. And one important thing, they are very easy to use, they are very easy to interpret, and easy to implement in your workflows. I'm not going to talk about Spectronaut today because we will have enough of that, but I wanted to highlight our solution for target proteomics, SpectroDIA. SpectroDIA is an unmatched solution for targeted proteomics, especially for high throughput studies. It has a very smart peak-picking machine learning base, and we control FDR for these high throughput targeted proteomic studies. We also have SpectroMine, as I said, that's our solution for label-free quantification in DDA mode, and also for isobaric label quantification and label-free quantification in DDA mode. One thing that is particular of our solution is that it's outperforming most solutions in the market in terms of number of IDs and speed. If you are interested in our software, in any of our commercial software, you can have a free trial guided by our experts of 30 days. We offer tiered pricing for different types of institutions, for academic organizations, academic core facilities, and industry customers. We offer discount if you get a bundle of them, and we also offer different licensing modes to fit your budget. If you're interested, please visit us. Here you can visit us at our booth, number 402, or you can also go in our website and you will find your way through the trial. So apart from our commercial software, we also offer a solution, a software that is free for monitoring your mass spec facility. It is based on the IRT kit, the readouts that it gets. Most of them are based on the IRT kit. You need to have it in your samples for the software to run. And you get readouts almost in real time, so you can react fast if something goes wrong in your facility. You can also set your individual threshold, and it's very nice tool to monitor your facility. Also, I wanted to highlight our quantification kit for plasma proteomics. So for you doing plasma proteomics, we have PQ500. PQ500 is a kit with standard cis peptides. We target more than 500 proteins in plasma, selected covering several diseases and quite a big order of magnitude. And basically, PQ500 is used for having absolute quantification of your targets, and also to get comparable results across different platforms and sites, for example. One example of how to use PQ500, you can use it also in DIA mode, but one example of how you would use it with SpectroDIA is to do a PRM. You spike your kit with your sample, you use the SpectroDIA plugin for doing the calibration methods, you run your calibration method, then you run the analytical method, then with SpectroDIA as well. Then so you get the best method, acquisition method with the help of SpectroDIA. You can get that method out, you run your quantitative runs, and then you analyze your data with SpectroDIA. So SpectroDIA really helps you in every step of the optimization workflow and to get the best of your PRM data. And with that, okay. We also have a couple of, actually 4 posters in this conference. We have one by Marco Tognetti. We have also one by Ino Karemaker. They both are highlighting our platforms through discovery using Spectronaut. We also have a poster by Lukas Reiter, same highlighting discovery through discovery and Spectronaut. And we also have a poster by Roland Bruderer, highlighting through discovery and Spectronaut. So if you want to know even more results gotten with Spectronaut 17, you should also check out those posters. And with that, I finish my introduction, and I give the stage to Lukas Reiter. One thing I want to mention, we will have a Q&A session at the end of the seminar, so please, if you have questions, hold them there, and please ask them afterwards, okay?
Good morning, everybody, and welcome to our Spectronaut 17 launch breakfast seminar. I'd like to talk a little bit more about what we did, and happy to be here in Cancun. So after our Spectronaut 16 release at ASMS this year, we quickly made a lot of progress in the development of our Spectronaut 17. And ASMS, which was still very far away, felt like we didn't want to wait until ASMS 2023 until we would release Spectronaut 17. So we decided we would go for IHUPO in Cancun to make an early launch of Spectronaut 17 and provide it to our users early on. So what's new in Spectronaut 17? It's actually very easy. It's what we call directDIA Plus. And for those who don't know exactly what directDIA is, I would give you a little introduction of what we understand directDIA is. So normally, so this is not directDIA, this is what people did for many years to get optimal results from DIA data. So they would take their samples, they would fractionate them, they would build a library from that, what we call deep project-specific library, and they would use that library to analyze the data and get really optimal results from the DIA data. But this library generation step was very tedious and was probably the most disliked feature of DIA, and also what prevented a lot of people to move from DDA to DIA. Now with directDIA, it's a much more direct way of analyzing your data. You simply acquire your DIA runs, and instead of making this library, you just use a FASTA file like you're used from data-dependent acquisition to analyze your data. So it's much more straightforward. Now, as I said, what's new in Spectronaut 17, it's directDIA Plus, and here you can see the improvements we get on thermo instruments. So on precursor level, we get really significant improvements of more than 30%, on protein more than 10%. Then it's even better for timsTOF data from Bruker. We get 62% improvement on precursor level and more than 20% on protein level. And then on SciX, it's even better, yet better again. We get basically a doubling of the precursors and more than 40% of proteins on the protein level. So really, really substantial improvements. These are the biggest improvements we ever had since the launch of directDIA, roughly 5 years ago. So, of course, identification is only one part of the story. Usually you are also very interested in quantification, and the way we usually analyze quantification, I want to describe on this slide here. So we have this standard set of samples that we generate by mixing proteomes together in different ratios. This gives us 2 proteome mixes. We acquire them in several replicates on a specific platform, analyze it with Spectronaut, and do the statistical testing for differential protein abundance. And then the last step is we take this list of ranked differentially abundant proteins according to p-value, and we plot them, and you can look at the number of true candidates, so known differentially abundant proteins, versus the candidate list length. And a really good measure to benchmark the performance is to take the number of true candidates you get at a certain error cutoff. So this is a very robust measure then if you do that. And a typical cutoff would be if you take, for instance, 5% error rate. So this is the benchmarks I'm going to show you afterwards. So here we ran such an experiment on a thermo platform. Here you can see basically quantitative results. But now if you really want to know or really want to compare quantitatively different workflows or analysis, here you can see the comparison of Spectronaut 16 to Spectronaut 17. So we also get a very, very significant improvement in the quantification performance with directDIA Plus. Now, you may also wonder how directDIA Plus performs in terms of deep project-specific libraries, and this is what you see on this plot here. So the baseline here corresponds to Spectronaut 17 and always using a very deep, highly optimized library for these experiments we are using here. And you can see that on the precursor level, directDIA Plus performs better than using these deep project-specific libraries, whereas on proteins, on protein level, it's roughly the same. But what I'm going to show now is actually really, really interesting. So here you see, again, this quantitative benchmark. And you can see that compared to these project-specific libraries, directDIA does a really, really good job. So directDIA is really a highly quantitative workflow. And there are several reasons for that. So one reason may be that you actually get more precursors. This gets you better protein quantities. But another reason is also that we see way less missing values in this data type. So this allows you to do better statistics and get better quantification. I also want to show this slide here. directDIA is a really versatile workflow. So we can look at you can look at your data with many different workflows and also different search space sizes. So in terms of bioinformatics, it makes a huge difference whether you have a 100-fold smaller or a 100-fold bigger search space. And I listed here a number of different experiment types and different workflows with vastly different search space size. You can see these search spaces here plotted on the right for a human proteome. So you can see that a tryptic digest is teeny tiny compared to, for instance, a phospho search space or an unspecific digest search space that you would maybe do in a peptidomics experiment. And directDIA is suitable for all of these. So if you're doing unspecific searches, you need a powerful workstation, but it works really, really well as well for these kind of workflows. So it's a very versatile tool. We also put a lot of effort into our AI models that are in the Spectronaut, and here you just see some summary statistics of what we did since the Spectronaut 16 release. So we tested more than 800 models with more than 60,000 epochs trained and close to 1 billion parameters optimized in sum on all of these models. And I'm going to illustrate what all this work is about a little bit in these examples here. So I'm making the example of retention time prediction, which is still very useful in these workflows. So let's assume you digest your proteins with a specific protease. You get a certain population of peptides, and you chromatographically separate them on a system and measure them afterwards. So let's say you would, I will go back. So let's say you generate your training data, you train your model, and it is able to predict retention times in this kind of system. But then let's say you do a different workflow, you use a different protease. Suddenly you get a different population of peptides. And what this is called is a domain shift in machine learning. So you train your model on one group of peptides, but then you apply it to another group of peptides. You will get slightly suboptimal performance of this model if you do that. But there are also other things in proteomics we do that are not so optimal for this kind of way of working, which is you can change your chromatography. Maybe you switch to a micropack and you run your experiment like this. But then again, this is what we call in machine learning a mechanism shift. So you are looking at the same peptides, but with a different solid phase, and the physicochemistry is slightly different. So your model again might not perform optimally on this. And in Spectronaut 17, we have put quite a bit of effort into improving the models to cope with that. And here you can see we made an experiment on a very different kind of chromatography. So it's a very different solid phase we used in this experiment. And you can see that for nowadays standards, you always see these plots on the holdout data sets where the performance is really, really high. But here we have this mechanism shift, and you can see that the model is not performing so well anymore. In Spectronaut 17, we have a model that is able to cope with that and gets double the performance, which makes a very big difference, as you can imagine. So we also put really a lot of effort into testing our releases, and here you can see a bit how this is structured. So we basically have sort of 3 phases. The first phase is where we perform a lot of automated testing, nightly and weekly benchmarks that are performed fully automatically. We look at really high number of experiments in these tests. We look at many different characteristics, protein coverage, quantification, also the validity of the FDR. And then the second phase is when this is a more semi-automated process, closer to the release, when we would look at particularly large experiments. They are oftentimes special in the way we analyze them. And there we again look at similar things, but also at the scalability and again at the FDR validity, because controlling the FDR in big experiments is particularly challenging. And then before a release, we have more manual steps. We share the installers with collaborators, for instance, with Jesper. We get very important feedback from our collaborators. And we also have internal early adopters in the R&D group that look at the releases and give feedback. And we also perform manual UI testing. That's something that is not very liked, but is very difficult to automate. And then we have our release. So we put a lot of effort into our releases. So this I was interested in. I asked my team to generate the plot for that. So how did the library way of analyzing the data and directDIA evolve with releases of Spectronaut? And here you can see the results of that analysis, which I found very interesting. So you can see that there were really dramatic improvements over the years, roughly last 5 years. But directDIA finally overtook the library way of analyzing the data, which of course we were super happy to see that. And so nowadays, so in total, we got more than 100% improvement over the years, and this is for thermo data. So on other platforms, it's probably even more. But what is really striking, and that's why the title of my talk, libraries you hardly need to use anymore nowadays with Spectronaut 17. And with this, I would like to go into a few applications. So the first one is an application from our own laboratory. Here we wanted to basically generate a protein expression atlas across different human tissues. We acquired these 22 tissues on our True Discovery platform and analyzed it with Spectronaut 17 and directDIA+. And here you can see the results of that. So we were super impressed by that. We basically quantified 8,000 proteins across all the tissues, around 12,000 proteins on average per tissue, and more than 16,000 proteins cumulatively in the whole atlas. So we basically had to get nowadays close to complete proteome profiling using directDIA Plus without any libraries, only with 22 runs, which is really very impressive. Then some data from a single cell application node from Bruker and Celanine. Again, analyzed with Spectronaut 16 and Spectronaut 17. And also we show here the data from the white paper with using a deep project-specific library. And again, we see very big improvements, and interestingly, particularly for the single cells, so which we explain by the fact that single cells show the highest variation in their proteomes. And this is particularly beneficial for not making a library because you capture the proteins actually directly from each individual sample. So again, very, very nice improvements, and you don't need to make libraries for these sorts of workflows. And then the last application I would like to show you is from a poster from Roland. It's a biomarker discovery study in urine. We had 3 different cohorts, chronic kidney disease, bladder cancer, and matched healthy controls, 27 samples each. And we were super impressed by that. We profiled more than 12,000 proteins in this sample set, so we could go very deep nowadays into urine. And in the PCA, you can see that we get partial separation of these cohorts, which is really good to see, good indication that we can find biomarkers in these samples. And we found a number of known biomarkers from literature, but also many, many new biomarkers. And if you want to know more, you please visit the poster of Roland. It's on Wednesday. So where is the limit, you may ask? And excuse me. So there was this really great paper from the Mann lab in 2011, where they looked at how many of these MS1 features they could fragment with a DDA workflow. And here you can see the results of that. So they could identify roughly 1/10 of all the MS1 features they identified in these DDA runs back then. So this was a really, really nice study and a really nice way of looking at the data. And we did the same for a modern DIA run. So here you can see a modern DIA run. Interestingly, the plot hasn't changed so much, but what has changed, what is not so obvious, is that the numbers have all increased tenfold. So there's tenfold number of features and tenfold number of features identified. But the take-home message from this slide basically is that there is still a lot of untapped potential in mass spec data. So there's still a lot of unidentified features, but there is, so there's also a lot of potential for quantification still. And yeah, with this, my summary slide. So with Spectronaut 17, we significantly improved the identifications and the quantification. It's a much simpler workflow. You usually don't need libraries anymore. And it works optimally with very different kind of workflows. So with this, I would like to thank my team, the whole Biognosys team, the collaborators like Jesper, who is giving the talk here. It's great to have him here today, and of course you for your attention. And we take questions at the end. So thanks.
Thanks, Lukas. Now we give the stage to Jesper Olsen. Looking forward to your presentation.
Yes. Okay, yeah, so first of all, thanks for the invitation to come here and present some of our data from, we were fortunate enough to get early access to the new Spectronaut 17. And I will try to share some of the analysis that we have performed. So in our lab, we try to do as many things as automated as possible. So all the data that I will show you has been, basically all the sample preparation has been done using the protein aggregation capture method on the Kingfisher Flex robot. We run all the samples with the EvoSep 1 system connected to the Orbitrap Explorer 480. And then we've used the Spectronaut with the directDIA analysis. And we also typically use a species mix to assess the quality of our results, such that we can look at both the identifications and the quantification accuracy at the same time. So we use a 3-species mixture consisting of HeLa cells, yeast cells, and E. coli cells mixed in different ratios. So you can see we have the E. coli and yeast in up to 9-fold different amounts in the different samples. And analyzing this data with Spectronaut 16, we are a little under 7,000 protein groups that we can identify in total. You can see it's mainly human proteins that we identify, since this is the major part of the mixture, but we also identify more than 1,000 yeast proteins and roughly 700 proteins from E. coli. But when we run the same sample now with Spectronaut 17 with directDIA, we can see that we increase the numbers by roughly this 10% that was mentioned by Lukas earlier. So especially for the yeast protein and human proteins, we see quite a significant gain in the number of proteins that we can identify. But more importantly is, of course, to look at the quantification, if that is impacted by these additional peptides and proteins that we see. And basically, we can see that the performance between Spectronaut 16 and 17 is exactly the same. So they are really on par in terms of the quantitative accuracy. Then we thought to maybe make a more challenging sample to analyze and benchmark this new Spectronaut 17. We used our offline high pH reverse phase fractionation system, where we collect a lot of offline fractions, so typically in the order of more than 40, and then compare basically the quantitative and identification performance by analyzing both single-shot DIA, but also fractions collected. In this case here, we collect up to 48 high pH reverse phase fractions that we then analyzed with both DDA and DIA. We also pooled some of the fractions, such that we end up with only 6 fractions, and analyzed those with DIA, and then performed single-shot analysis with either 100 nanograms, 10 nanograms, or 5 nanograms of input amounts. And first, we could see that when we analyze these data, that the new Spectronaut 17 gives us the highest results in the DIA mode compared to the DDA modes. And more importantly, you can see that we have a large fraction of proteins that are unique to Spectronaut 17. But more strikingly is that if we look at the number of modified peptides that we can identify from these type of samples, that we can see that we basically go from less than 150,000 different modified peptides to almost 175,000 unique modified peptides using the new Spectronaut 17 with the directDIA type of analysis. So we are really happy with this. This allows us now to start to look at also modified versions of peptides in the DIA analysis. And again, the fraction of unique peptides is significantly higher here with Spectronaut 17 in DIA mode compared to the other analysis. So we also compared Spectronaut 16 and 17 with DIAN with these samples. And for the number of proteins, we can see that DIAN provides numbers that are comparable to Spectronaut 17, so just below 9,600, whereas Spectronaut 17 is just above 9,600. But also in terms of the number of peptide groups that we can identify, it seems like Spectronaut 17 with this deep fractionation is very comparable to what we get out of DIAN. But more importantly, if we look at these small spectral libraries, so these just 6 different offline fractions that we have collected and analyzed them with either Spectronaut 16 or 17, we can see that from the single-shot runs that we actually identify more proteins when we use the smaller libraries compared to the larger libraries. And this is in particularly the case when we use Spectronaut 16 and 17. We can see if we run with the directDIA that Spectronaut 17 again performs the best. If we run in this so-called method evaluation mode, where each file is searched separately, we can see that the numbers are dropping a bit for the 5 nanograms and the 10 nanogram loads, but actually for the 100 nanogram loads, still the Spectronaut 17 seems to outperform all the previous generations. And this is even more striking when we look at the number of peptides. We can see that Spectronaut 17, again, with this 6 fraction library, can identify more than 40,000 unique peptides. And in particularly in this evaluation mode, we can see that the number of peptides are significantly higher. So when we compare between DIAN and Spectronaut for these single-shot analysis, we can see that DIAN typically, in the best conditions, can identify around 35,000 unique peptides, whereas in the direct mode, it drops down to 28,000 without the library searches, whereas Spectronaut 17 it gives us close to 40,000 unique peptides, and in the library-free mode, we are up at more than 30,000 unique peptides. So our lab is, of course, also doing a lot of phosphoproteomics analysis, and in this case, we basically perform the phosphopeptide enrichment also in the Kingfisher Flex robot. So it's basically in line after the pack digestion, where we can do the titanium IMAC enrichment before analyzing the samples again on the Orbitrap Exploris 480 system. And in this case here, we can see that when we run with Spectronaut 16 from a data set like this, that we typically end up with roughly 13,000 phosphopeptides identified, whereas in the method evaluation mode, we are down to 9,500. But if we use now the new directDIA method, we can see that we identify more than 15,000 unique phosphopeptides in these samples, and close to 10,000 or even more with the directDIA approach. So we also thought if we wanted to try to now use a really big phosphopeptide library to see how that would impact the results. So we collected actually using 2 different offline fractionation methods, one with our standard collecting 24 fractions on the Dionex system, and one where we collected 24 fractions from the Spider fractionator. And surprisingly, we actually see that the overlap between these 2 systems are only in the order of roughly 50% of the total identification. So altogether, we identified more than 100,000 modified peptides from this analysis. And then using these libraries with the new Spectronaut 17, we can see that we can dramatically increase the number of phosphopeptides identified in these samples, actually going up to more than 23,000 phosphosites on these in the same sample, simply using this very extensive library as for the search. And again, when we compare with the Spectronaut DIAN, we can see using the same library strategy that the number of phosphopeptide precursors are actually significantly lower than what we can get from Spectronaut 17 without using a library. So comparing between DIAN and Spectronaut 17, we can see that Spectronaut 17 gives us much better and much higher number of peptide identifications, both in the direct mode, but also with the library settings compared to DIAN. So with that, I hope I've been able to show you that for low input samples, we see that Spectronaut 17 is really outperforming DIAN and Spectronaut 16, that for high pH fractionated samples, DIAN seems to perform similar to Spectronaut 17 in terms of the number of identifications. The spectral library-based analysis seems to work best when you have a reasonable sized library. And for phosphoproteomics, we really see that Spectronaut 17 completely outperforms DIAN in terms of number of identifications. And with that, I would just like to thank the people in the lab who did the work, and this was especially Silu Ye, postdoc in the group that did all these analysis, and thanks to all the collaborators, and thank you for your attention, and I guess there will be time for questions afterwards. Thank you.
So now it's time for questions. Please, I ask the speaker to take a seat. And now it's your turn. I hope you remember all the questions you accumulated. Please go ahead.
Jesper, impressive presentation.
Thank you.
Your lab also is well known for other modification like ubiquitination. Any ideas how it works with the 200 other modifications, as well also glycosylations?
So, we haven't tried. Can you hear me? This one's on. Okay, good. Yeah. So we haven't tried yet to do like an extensive search with many other variable modifications, but it actually seems like this new directDIA workflow enables you to look for at least 5 or more variable modifications at the same time. So if you can look for all the, let's say, major post-translational modifications. Glycosylations is obviously very challenging to look for, but acetylation, methylations seems to work really well.
Good morning. Thank you very much both for the presentations. I have 2 questions. The first one's for Jesper. It's a lot of phosphopeptides, which is absolutely brilliant, but my question is about false positives. And do you have any feel for how many of those actually are correct, are putative, are wrong?
So, the nice thing with the Spectronaut way of doing phosphoproteomics is that you do not only get the identification of the peptide, you actually also get the localization of the phosphorylation sites in the samples. And you can try to do all kind of tests to see how reliable the identifications are using whatever, for example, we've made use of samples where we have spiked in synthetic standards where we know exactly where the phosphorylation sites reside. And typically we see that the error rates are, let's say, in the low % range in terms of identification and localization of the phosphorylation sites.
Thank you. My second question relates, I guess, to serial searching, and it's a question for both of you. Do you think there'd be any benefit in going through looking for non-modified peptides, then phosphopeptides, then acetylation, whatever, and extracting those portions of the data out? Do you understand? Am I clear?
I guess that this would be a more question for Lukas.
Yeah, if I understood correctly, so you are asking whether you should also look for the non-modified peptides if you have a modified peptide workflow, like phosphoproteomics.
Yeah, I mean, there are other search engines which do this sequential manner. It kind of, not very much, but it starts to shrink your search space.
Yeah, I would always recommend to go for the full search space and not limit yourself to only a sub part of the search space. That's, in general, it makes the search space bigger, but you should get better results if you do that. So I would recommend to do that. Yeah.
Thanks, both.
Thanks a lot for the nice presentation. I also would have a question to Jesper. Yeah. Did you also look at the quantification of phosphopeptides?
Yes, and basically we can see that performs the same as for the species mixture type of experiment, that when we use these samples where we know what to expect, we don't really see any difference in the quantification between Spectronaut 16 and 17, but we see this dramatic increase in the number of phosphopeptides that we can identify. So yeah, we're very excited about this, obviously.
Cool, thanks.
I would like to, first of all, thank you for pushing the field and learning more and more about proteomics data, or helping us to learn. And I would like to understand a little bit more what actually helped you to improve Spectronaut. What are these new peptides? What are the features? And to learn a little bit why, what is this behind black box in Spectronaut, why it is doing so great suddenly.
Yeah, I mean, one part is what I basically showed. So it's really also the deep learning has really impacted the field dramatically, and we can do things that we couldn't do 5 years ago. So that's certainly a big part of these fast developments you see in the past years. So being able to predict retention time really accurately, being able to predict the fragmentation really accurately, that's certainly part of the improvements, but it's many other improvements too. So.
Thank you for the presentations. There are many papers that are comparing Spectronaut and DIA and other softwares, and the usually conclusion is that they are not comparable because there are major differences in the algorithms and so on. But I also see that you made some comparison. What actually did you do to make it like similar to compare in the end, and what one should keep in mind when compared to softwares?
Yeah, I guess that I can start and then you can follow if you need. Yeah, so what we did was, of course, to do the search for using the same data set. Then we afterwards look at how is the FDR at the protein level, how do we need to filter at the protein level in order to basically achieve the same FDR for the two methods. We often use this kind of decoy strategy where we, for example, with the 3 species mixture, where we have human and yeast and E. coli, then we add a 4th database, for example, C. elegans or maize, and then we can see, based on that one, we can estimate what is actually the true false discovery rate at the protein level, and that's where we can see it's often a bit inflated, especially in case of DIA.
Thank you.
I mean, I can also maybe add a little bit to that. So we also do comparisons and benchmarks, and making, because you hinted a bit towards that, making benchmarks across different tools is sometimes not so easy because there are different settings surrounding FDR, surrounding protein inference, surrounding other things. So making a comparison really, really fair is not that trivial, actually. So we also see that ourselves.
Thank you for your presentation. I have a question about data point. How you can maintain good number of data point for low input and phosphopeptide? If we sacrifice the data point, we can increase the number. But usually, how many data points do you get from very low input or phosphopeptide?
So you mean in terms of how many data points across the peaks? Yeah. So this, of course, highly depends on the chromatographic performance of your system, the scan cycles that you're using for your DIA windows, and these things just needs to be matched very well. Obviously, low abundant peptides will generally tend to have fewer points across the peaks than high abundant peptides. So you will see, let's say, a hit in the quantitative accuracy on the low abundant peptides. I don't know if you have...
No, I would have a question for you, actually. So I was wondering, so samples often behave based on their protein abundance distribution. For instance, cell lines behave different to plasma because of the protein abundance distribution very different. How would you say is a phosphopeptide sample, what is it most similar to what other samples like?
Yeah, so I think in many ways, actually, it's more similar to a plasma proteome analysis, where we typically see that we have some phosphorylation sites that are extremely abundant and many phosphorylation sites that are very low abundant. Maybe somewhere in between the two, actually, in reality. And that also really depends on the input amounts that you have for the phosphopeptides, and often you can see that phosphoproteomes from cell lines are very, very different from phosphoproteomes from human tissue patient material.
Okay, thanks. Interesting.
Hi, thanks for the nice talks. I had a question for Lukas, and it's something you alluded to at the end of your talk about non-identified isotopic clusters. So I guess my question is, how much more can you really squeeze from the same raw file with search engine optimization? I mean, it seems like DIA and Spectronaut are kind of on the same level in terms of normal tryptic peptides, but can you really squeeze, another 100% from the same raw file by just tweaking the search algorithm, or are we kind of at the limit of how far you can go?
Yeah, that's a good question. I also ask myself the same question. If you looked at these curves that I shown in one of my slides, if you would just extrapolate that, then it should go on very steep. But I expect certainly that there will be more improvements in the coming years, that I expect for sure. But at some point, the curve will probably flatten out a little bit. But there is still also a lot of work that can be done on the quantification, which will also have huge impact.
Thank you for a really nice presentation. I was wondering how does the Spectronaut's prediction model compares to the ProCit?
To ProCit?
ProCit, yeah, the proteomics
okay.
DP.
So we didn't do extensive benchmarks there, but if you look at, also in the paper, you can see some benchmarks on holdout datasets, and we would be in a similar range on those holdout datasets, maybe sometimes a little bit better because this data was also published many years ago. But as I've shown in my slides, what is sometimes more important is not the performance on your holdout dataset, it's more the performance on datasets out in the wild that matters.
Thank you.
Great presentation, thank you. So my question is for Lukas. You mentioned that directDIA plus did better than library generation. Is it true also for hybrid libraries? Did you do any analysis there that directDIA plus and library, are they going to perform better than library free?
You wanted to? I can say something here. So,
yeah.
In terms of identifications, you may still be a bit higher with a hybrid library approach. I would say in terms of quantification, there will be hardly any difference in real life experiments. Let's say if you have some biological variability and so on, your quantification performance will be basically the same.
Do you know roughly how much better you can get in identification with hybrid system?
No, that I couldn't tell you.
Thank you.
Question for Lukas. You mentioned different levels of performance improvement for different vendor instrumentation with Spectronaut 17. Can you talk a little more about what you think is driving those different levels of improvement in terms of number of IDs?
Sorry, I didn't understand the very first part. Can you repeat that, please?
Yeah, so the thermo instrumentation, Bruker and SciEx, you showed different levels of improvement.
Mm-hmm. Yeah, so I mean, one explanation there is that we are working mostly with thermo data. We may have optimized the algorithms more for this data. And also the other platforms are much younger, and that's maybe another reason. But TOF data tends to be also a bit more complex. So for the timsTOF, it's 4-dimensional. That's one more added complexity. And you generally get more spectra, so it's probably more challenging to work with. And that's probably why there's also more potential working with that data.
Thank you.
Sorry, me again. You have done a quite extensive comparison with Diane about numbers of identification. I'm a little bit missing the accuracy of quantification in the comparison of these two software packages.
So, sorry, you asked whether we did comparisons?
Yes, with Diane, yes, and the quantitative comparison.
The quantitative comparison?
Yeah.
We didn't look into that so much, I have to say. So we were comparing identification, but we saw, so as I said, so it's difficult to compare proteins between the two tools, but we saw a slightly better performance with Spectronaut in general on the precursor level, or actually I would say a 2-digit better performance on the precursor level. And in terms of quantification, they are rather similar, but we didn't look into that too much.
Any more questions? Yes.
Hi, thank you for your presentations. I have a question regarding missing values. So from the phosphocyte numbers you showed, how many of those phosphopeptides, have, let's say, less than 50% missing values across all your samples? Yeah. And how does that compare to DIAN performance?
Yeah, so that's, of course, a very important point. And usually we see, if you are analyzing samples, like in this case here, that are actually the single-shot runs are very comparable because they basically consist of the same digest that we analyze, and then the missing values are very low between the data sets. But as soon as we start to look at biological samples with much higher variability, then we obviously see a significantly higher number of missing values. it's not at the order of 50%, but it's typically maybe in the range of 20 to 30% if you have data that are significantly different. If you do like a big time course experiment, look over many different hours of stimulation of phosphodata. I don't know if you have more quantitative numbers on this.
For phosphoproteomics, no. I wouldn't have the numbers in my head, but I would also expect quite a bit of biological variation.
Yeah.
Do we have any more questions? So if that's not the case, I want to thank you all for being here, really, for staying until the end, and for such an interesting question session. Thanks to our speakers. Last applause to them, please.